All right. So congratulations, everyone, for making it to the final NETS 412 lecture, or 4,120, as we say now. And so for most of the class, up until like last lecture, if you recall, we've sort of been game theorists that had like a learning theory problem. You know, maybe we knew a little bit of learning theory and we made productive use of it. You know, we derived and used the polynomial weights algorithm to prove the min-max theorem and to think about dynamics in games and to give online auctions. We studied bandit learning algorithms like the upper confidence bound algorithm to derive dynamic pricings. And in general, we sort of took advantage of things like statistical estimation and random sampling auctions. And then starting like last lecture, we sort of transitioned from being game theorists with a learning theory problem to learning theorists with a game theory problem, like rather than reducing problems in mechanism design to problems in statistics and machine learning that we could solve. Last lecture, we started from sort of this purely learning theoretic problem. We wanted to make predictions, robust predictions against an adversary that had some nice property that were calibrated in the worst case. And we sort of derived algorithms using what we knew about game theory, in particular by reducing to the min-max theorem. And so today I want to do something similar. I want to start with a purely machine learning problem, this boosting problem. How do you take a predictor that is, okay, a little bit better than random guessing, and combine predictors of that sort into predictors that are actually quite strong, that are good at making predictions. And I want to solve this problem using what we know about game theory. So what I want to do today is sort of derive from scratch this sort of class of machine learning algorithms called boosting algorithms that you might have encountered if you've taken a machine learning course or played around with things. They have names like AdaBoost or gradient boosting. And the general idea is, like if you've got some simple method, like the ability to learn shallow decision trees or something that is sort of kind of non-trivial, like better than random guessing, but not great, how do you use that method, maybe run it a few times, and combine the simple rules you've learned into a single model that is substantially more powerful, substantially more predictive? Okay, that informally is the boosting problem. And so, let me try to give you like a crash course in machine learning. This is stuff you might have seen before if you've taken a machine learning class. So just to sort of fix the setting, we're going to think about data sets that consist of labeled examples. What is a labeled example? Well, it's got like some features. Maybe if it's like an image labeling problem, the features are like the pixels in an image. And it's got a label. The label could be anything. In this class, we'll sort of think about binary labels. So the label says, is the thing in the image like a cat or a dog, a hot dog or not a hot dog? And so, for example, although these choices aren't too important, oftentimes like the features will be things like vectors of numbers. Like that's the case if you have like an image classification problem, right? Like then the features you have available when you're trying to classify whether something is a hot dog or not a hot dog are like the pixels in the image, which we can encode with real values. And then we've got like a binary label, for example, where 1 denotes that the image is a picture of a hot dog and 0 denotes that it's not. Okay, so we're given a data set, which is a collection of n such labeled examples. Okay, sampled from some distribution, presumably. And our goal, right, so we're given a bunch of examples together with, like the answer, the thing that eventually we'd like to learn to predict. Does the image contain a hot dog or not? But our goal is to learn to predict labels on new examples we haven't seen before. And to do that, we need to learn some mapping that looks at only the features and tries to predict the label. Takes as input like the pixels of the image and tells us, does it contain a hot dog or not? Okay, we'd like to do this in a way that has high accuracy. So there's different ways you could measure accuracy, but I want to think about maybe sort of the sort of simplest one, the one you'd maybe think of first, which is just how frequently do you get the answer right? Okay, so suppose we've got some predictive model, takes as input images, outputs labels. The accuracy on that model on a data set is just the fraction of points for which our model correctly predicts the label. Okay, so it's just like the average over all of the points in our data set of the indicator that when we apply of the event that when we apply our model to the features, okay, the model doesn't get the labels, the prediction of our model is correct. It actually is the label. Okay, so like on any particular example, this is 1 if we predict the label correctly, it's 0 otherwise. And so this average, the accuracy of our model on the data set, is just the fraction of examples it correctly predicts the label on. Now, this notion of accuracy just sort of uniformly weights all of the points. It's sort of saying all of the points are equally important. I'm just measuring like the unweighted fraction of points that the model gets correct. But you can also imagine defining a weighting that sort of informally says some of the points are more important than others. Okay, and so we could also imagine, given a weighting that you can think of as a distribution over the points, asking what fraction of points does our model correctly label, not under the uniform distribution, but under this other weighting, under this reweighting. Okay, so I can also talk about the accuracy of my model on a data set under some weighting, which is just the same thing as the accuracy of the model, except instead of giving every point the same weight, 1 over n, different points could conceivably get different weights. Okay, so these are both, like the weightings, this should be like a distribution over the points. So in either case, these numbers are numbers between 0 and 1, like what fraction of the points do we get correct? If there's no weighting, it's just what fraction of the points under the uniform distribution do we get correct? If there is a weighting, then we're asking what fraction of the points on this reweighted data set where we've said some of the points are more important than others. Okay, does that make sense? We've got some model, we can like ask how accurate it is on our data set. Like what fraction of the labels does it predict correctly? Okay, I just want to mention up front something that I'm basically going to ignore for this lecture. So that an important statistical aspect of machine learning is, of course, that my goal is not to predict the labels of the points in my data set. I already know the labels of those points. My goal is to predict well on new points that I haven't seen before that are somehow, statistically similar, that are drawn from the same distribution. Right? Because actually, like if I just wanted to predict the labels of the points in my data set, I could do so by just writing like the labels of all of the points on my hand. And whenever you asked me about a point in my data set, I'd like look it up and I'd always be right. And I wouldn't really have learned anything. That wouldn't be a good model for points I haven't seen before. Okay, so our goal is not really to minimize or maximize accuracy on the points in the data set. We'd really like to do this for sort of other points. And sort of informally, there's a whole theory for how to do this. Informally, we want to make sure that the rule we're coming up with to predict labels produces simple rules somehow, rules that can be expressed more concisely than just writing down all of the labels on my hand. Okay, so like if the description length of your prediction rule is smaller than the description length of the data, then it must be that you have learned something that generalizes to new examples. The approach we're going to derive in this lecture has this property. So it is a good learning algorithm. It's not just a lookup table. But I'm not going to talk about it. We're just going to talk about the algorithmic aspect in this lecture. But just like as a good piece of culture to remember, the goal in machine learning is not to predict the labels in your training data set, which you already know. It's to predict the labels you haven't seen before. And in order to do that, it is sort of necessary and sufficient to compress the data. You want to learn something that is simpler than the data itself. Okay. So a little bit more setup. We're going to learn some rule. What's that rule going to look like? Well, let's say that a hypothesis class H is a collection of rules we might learn. Okay, so it's just a collection of predictors, a collection of functions of the sort we're trying to learn, each of which map features to labels. Okay, so there's all sorts of different ways we could imagine trying to predict, given an image, does it contain a hot dog or not? And a learning algorithm is just an algorithm. This is the kind of thing we'd like to design that takes as input a data set, takes as input a data set of labeled examples, and outputs a hypothesis. Right? It takes as input data, it thinks about it, and it somehow outputs a rule designed to predict the labels given the features. Okay, and remember we talked about, and hopefully this rule has, the predictive rule you learn has high accuracy. And remember we talked about accuracy, not just, uniformly over the data set, but in this sort of weighted way. We can sort of weight different points so that they contribute differently to the accuracy. And so a weighted learning algorithm just takes as input a data set and a weight vector telling us how important each of the data points is. And it outputs a hypothesis, so a rule for predicting labels given features that hopefully has high accuracy under this weight vector. Okay. So I want to point out that if we're in the binary prediction setting, if there's only two labels, if you're, the image either contains a hot dog or it does not, then it is not interesting. You should not be too proud of yourself if you come up with a learning algorithm that finds hypotheses that have accuracy less than 1/2. Right? I mean, there's only two answers. The label could be 1 or 0. The accuracy is just the fraction of the time you get the answer correct. So if you get the answer correct less than half the time, this is worse than you would have done by random guessing. Right? If I just ignore the data and flip a coin for every example, my accuracy will be 1/2. I'll get half of the answers right. So it's not interesting to get accuracy less than 1/2. What I'd really like is to get accuracy something like 99%. I'd like to find a good learning rule that almost always is able to correctly predict the underlying unknown label. But what I want to think about is, the space in between. Suppose I'm doing better than flipping a coin. I've designed an algorithm that consistently beats coin flipping, but can't get anywhere near 99% accuracy. Okay, so suppose what I've got is an algorithm. It's like learning some simple rule, like a linear regression or something. And what it can do is it can reliably get accuracy 51%. Can reliably do a little bit better than random guessing, no matter what data set I give it. Okay, what can I do with this? Something that reliably does better than random guessing. Okay, we're going to talk about this. An algorithm that has this property that can sort of reliably do just a little bit better than random guessing, but not very well, we'll call it a weak learner. And the question I want to ask in this lecture is, if you give me a weak learner, can I use this as a subroutine, hopefully in a computationally efficient way, to do something more like this, to get accuracy 99%? Okay. So we'll talk about this, in more depth, more formally. But are there questions at this point? We're thinking about a prediction problem, a binary prediction problem. Okay, given images, do they contain hot dogs or not? Accuracy 50%, since there's only two possible answers, that's trivial. I could do it by flipping a coin. suppose you give me an algorithm that is a little bit non-trivial. It can promise to get 51% accuracy, just a tiny, like a smidge better than random chance, what you'd get from guessing. Does that, is that a lot easier than getting 99% accuracy? Or is it basically the same problem? Like if you give me this weak learning algorithm, can I use it to get actually a strong learning algorithm? That's the question in boosting. So does the question that we want to ask and answer in this lecture make sense? Yeah. Say that again. So it's a binary prediction problem. So there's only two possible labels. In general, you could talk about like a k-label problem, in which case, like the random guessing benchmark would be like 1/k instead of 1/2. But in this lecture, we'll just talk about two labels. Good question. Other questions? Yeah. They could do better, but the only promise we have is that they get 51% accuracy. But maybe we get lucky and, on this data set, we get like 60% accuracy. Okay, so you could ask this question for, k-label problems. You could ask it for regression problems. In every case, the question is, if you give me something that does a little bit better than random guessing, can I turn it into something really good? But in this lecture, I'm just going to ask and answer this question for the binary prediction problem, two labels. Okay, does that make sense? Okay, so let's formalize this a little bit. So suppose we've got one of these weighted learning algorithms. It takes as input a data set and a weight vector. We say that this algorithm is a weak learning algorithm for the data set if for every weight vector I give it, it can always find a hypothesis such that the weighted accuracy on this data set is a little bit better than random guessing, at least 51%. Okay, it might sometimes do better than that. The promise is just that in the worst case, it's always a little bit better than random guessing. And you might say, am I trying to sneak in a fast one here? What is this weighted learning algorithm? Maybe you're used to thinking about learning algorithms that get training data and output hypotheses. What are these weights doing? The weights are sort of without loss of generality. So just to sort of say something quick about that. First of all, in almost any machine learning algorithm you've ever seen, you can just directly input the weights. If you're training a neural network, you're minimizing some loss function that is just the average of whatever your favorite loss function is over all of the data points, and you can just plug in the unweighted average with the weighted average, and the algorithm works exactly the same way. If for whatever reason you've got a learning algorithm that doesn't take as input weights, no problem. When I say here, input a data set and weights, what you do instead, right? What are the weights? They're just specifying a probability distribution over the data points in your data set. Just sample a new data set according to that probability distribution, meaning, given your data set and the weights, sample a bunch of points, where you sample each point proportional to the weight I've given it. That gives you just a new unweighted data set, feed that to your learning algorithm, exactly the same thing. So I'll speak as if the learning algorithm directly takes as input these weights, but that's just for convenience. Everything I'm saying would be true with just sort of an additional added notational burden if the learning algorithm only took as input data sets. Yeah. Yeah, the features are not weighted. It's the examples are weighted. So maybe, yeah, images of hot dogs taken at Coney Island are more important than images of hot dogs taken in grocery stores, something like that. Okay, other questions? Okay, so yeah, I'm going to talk about learning algorithms as if they take as input these weights. Many of them actually do. If they don't, don't worry about it. You can just sample a data set and everything works if the algorithm just takes as input a data set. Okay, so like, maybe it's a little, the name we've given to these algorithms is like a little bit leading, but weak learning algorithms seem kind of weak, right? Like the only thing they promise is that they do a little bit better than random guessing. If you just wanted to get 50% accuracy, you wouldn't have to do anything at all. You wouldn't have to look at the data. You could close your eyes, flip a coin. You wouldn't even have to look at the features of the thing you were making a prediction for. And, like we've got some machine learning algorithm, and the only, maybe it's like learning decision trees or something, and the only thing we can promise about it is that it does 1% better than random guessing would. Okay, so that doesn't sound great. Like it's not going to be a very useful algorithm in whatever your deployed hot dog application is. What we want really is something that makes predictions that we can rely on. We want something more like 99% accuracy. Okay, and so maybe like by analogy to weak learning algorithms, which get 51% accuracy, if something gets 99% accuracy, let's call that a strong learning algorithm. And the question is, like, is strong learning a harder problem than weak learning? I mean, like, seems like the answer should be yes, right? Like getting 99% accuracy seems harder than getting 51% accuracy. But it would be kind of interesting if the answer was no. Okay, and maybe like, what do we mean by get strong learning from weak learning? I sort of mean in the sense of like computationally efficient reduction. If you give me a weak learning algorithm, of course, in the other direction, a strong learning algorithm is a weak learning algorithm, right? Like 99% accuracy implies 51% accuracy. But the question I want to ask is, if you hand me a weak learning algorithm, can I necessarily use it as a subroutine in some otherwise computationally efficient algorithm? Just call your weak learning algorithm some modest number of times and get provably a strong learning algorithm. Okay, that would mean that the two problems of weak learning and strong learning are sort of equivalent in a rigorous sense. That if you can solve one, you can solve the other with only polynomial overhead and vice versa. Okay, so let's be ambitious in our definition of strong learning. I said we want 99% accuracy, but like, why are we leaving that last 1% on the table? Let's just go for like 100% accuracy. Okay, so let's say that a strong learning algorithm for a data set is one that like outputs a hypothesis that never makes a mistake on the data set. Okay, like gets all of the predictions correct. Okay, so this seems like a much harder problem than weak learning. Okay. But the theorem I want to prove, sort of one of the foundational theorems in machine learning, is that in fact, weak learning and strong learning, they're equivalent. Weak learning is actually no harder than strong learning and vice versa. Okay, so one direction's obvious. If I can always, solve machine learning problems with perfect accuracy, that means I can always solve them with 51% accuracy. But the surprising direction is that no matter what data set you give me, if there's an efficient, meaning like polynomial time, weak learning algorithm for the data set, one that can always guarantee 51% accuracy, then actually there's an efficient strong learning algorithm, okay, a polynomial time algorithm that can always make perfect predictions. Okay, so this is the theorem. What do you think? How should we prove this theorem? Yeah. Yeah, it seems like a good idea. We've done majority vote kind of stuff before. Okay. I guess like sometimes you can like guess the answers to like exam questions from the context in which they've been asked. And I guess, having given a prefix of this lecture about machine learning, but like in like an algorithmic game theory class, that's like a hint as to what the proof idea might be. The way we're going to prove this theorem is by using the tools we've developed in this class to study games. In particular, we're going to define an appropriately defined zero-sum game. We're going to analyze the value of that game. We know that zero-sum games have a value by the minimax theorem. And the way we're going to derive the algorithm that witnesses the statement of this theorem, the actual algorithm that is the reduction from weak learning to strong learning, will be via the computation of the equilibrium strategy in that game, which we know how to do with the polynomial weights algorithm. Okay, so that's going to be like the outline of the solution. We've got this basic sort of foundational problem in machine learning. We're going to solve it using, you know, our favorite toolkit from NETS 4120. Have you guys gotten used to all of the classes having like a 0 at the end of it? It seems like a waste of like the last digit, right? It's like always 0. So there's these banknotes from Zimbabwe during like periods of hyperinflation where they just added like 10 zeros to the end. I feel like the same thing's happening here. Anyways. Okay, so let's prove it. So we've got this weak learning algorithm A. Someone has handed this to us. And it's got some hypothesis class, right? Like, you know, you give it a data set. What it does is it outputs a hypothesis. The hypothesis class is the set of all hypotheses it might output, give, you know, like for any data set you give it. And so what I want to do is I want to define the following two-player zero-sum game. What do I need to do to tell you, you know, a two-player zero-sum game? I need to tell you who are the players. There's 2 of them. I need to tell you what are their actions, what's their action set. And I need to tell you what is the function that the minimization player wants to minimize and the maximization player wants to maximize. Okay, so first of all, you know, the minimization player, which maybe I'll refer to as the data player, their action set is going to be the set of labeled examples in the data set. Okay, remember the input to a learning problem is a data set consisting of n labeled examples, like images, so together with the label of whether they contain a hot dog or not. And so like the set of pure strategies for the data player, the minimization player, will correspond, you know, they've got n pure strategies. Each one corresponds to one of the labeled examples, and a mixed strategy for the data player corresponds to some distribution over those examples, like a weighting of the data set. And the action space for the maximization player, which I'll call the learner, that corresponds to the hypothesis class of the learning algorithm. Okay, so out of all of the hypotheses that the learning algorithm might output, like a decision tree of depth 4, for example, a pure strategy of the learner corresponds to one of those hypotheses, one of those models aimed at predicting labels from features, and a mixed strategy for the learner is a distribution over models, a weighting of the hypotheses. Okay, and there's a cost function that the minimization player, the data player, would like to minimize, and that the maximization player, the learner, would like to maximize. And let's try to put the cost function in correspondence with accuracy, right? Because, you know, like anthropomorphizing these characters a bit, right? Like the learner would like to maximize something. The natural thing he'd like to maximize is the accuracy of his prediction. Now, remember, a pure strategy for the data player is a labeled data point, a feature vector and a label. A pure strategy for the learner is a model, something that predicts a label given the features. And so let's say the cost, given a feature vector and a model, is just the indicator of whether the model chosen by the learner correctly predicts the label of the data point chosen by the data player. Okay, so for example, if the data player plays a mixed strategy, which is just a weighting of the data points, a distribution over the data points, the expected cost for the learner, the thing that the learner would like to maximize, is just the weighted accuracy of the hypothesis that he chooses. Okay, does that make sense? So we've set up like a zero-sum game in which the minimization player plays, well, if they're playing mixed strategies, plays distributions over the data set, so weightings over the data set. The maximization player, the learner, plays hypotheses or maybe distributions over hypotheses. And the thing that the learner would like to maximize is their accuracy, and the data player would like to play so as to minimize the learner's accuracy. Does the game make sense? The rest of the proof is going to be thinking about this game. So this is a good point. This is a good time to like take a moment to just make sure we all understand the game. Yeah. So remember, a zero-sum game is just one in which there's like a single objective function that one player wants to make big and the other player wants to make small. Right, because like why is it called zero sum, right? Like suppose both players have a utility function. Well, this is the utility function for the data player. They'd like to make it big, this is the utility function for the learner. This is accuracy. The learner would like to make this big. What's the utility function that the adversary would like to make big? Well, it's the negative of this because they'd like to make this small. And so if I sum up this and the negative of this, it's 0. Yes, but yeah, like when we've talked about zero-sum games, there's like, rather than talking about two functions that are, the negative of one another, it's easier to talk about like one function that the maximization player would like to make big and the minimization player would like to make small. Does that make sense? Yeah. Well, what does anyone really want? Like within the game, their objective is to minimize accuracy. Now, of course, like this is like an object we're constructing in the proof. Like in real life, there's no data player, but the data player, who is a character in the proof, yeah, they really want to minimize accuracy. Does that make sense? Okay. Other questions? Okay. And so, like, what do we know about zero-sum games? Like, the one thing we know about zero-sum games is the min-max theorem, which means that the game has what we call a value, right? Like in general, in games, we think about them when we think about Nash equilibria as both players playing simultaneously. In general, things could play out differently if one of the players went first instead. If like one of the players had to go first, commit to their strategy and announce it, and gave their opponent the ability to best respond, the opportunity to best respond. And the special thing about zero-sum games is that the order of play didn't matter, so long as everyone played optimally. Okay, so like in rock, paper, scissors, if I tell you up front my strategy, I'm going to like randomize uniformly at random between rock and paper and scissors, that does not give you the ability to exploit me, right? Similarly, like if I tell you that and you best respond, the average payoff in the game is going to be the same as if you told me your strategy up front, so long as it was optimal, randomizing between rock and paper and scissors, and I best responded. Right, and then sort of what the min-max theorem tells us is that's like a property that's true of all zero-sum games. If the minimization player goes first and announces their strategy and gives the maximization player the ability to best respond, the expected payoff is the same as if the maximization player goes first and announces their strategy and gives the minimization player the ability to best respond. And whatever that payoff is, since it's the same in both cases, we call that the value of the game. So the first question we can ask about a zero-sum game is, what is the value of the game? Okay, so, again, like, this is sort of similar to last class. What's really going on when we design a learning algorithm and we want it to have worst case guarantees is like we, the learner, are sort of going first because we're like committing to an algorithm. And then if someone's trying to like falsify that we have worst case guarantees, they might try to like best respond with knowledge of our algorithm, with knowledge of our strategy, trying to falsify those. But it's easier to analyze games often if we reverse the order of play in our imaginations and imagine the adversary goes first. Then we can figure out what the value of the game is, and that tells us how well we can do if we go first, because those two numbers are the same by the min-max theorem. Okay, so going through this exercise, I claim that the assumption that we have been given a weak learning algorithm, that there exists a weak learning algorithm, implies that the value of the game has to be at least 51%. Okay, let's think about it. Let's imagine the data player goes first. The data player is the one who wants to minimize accuracy. So we're looking at the min-max value of the game. First, the data player commits to a mixed strategy, a distribution over the data points. Then we get to look at that distribution over the data points, W, and best respond by choosing a hypothesis that maximizes accuracy. And the way we evaluate how well we've done is we compute the expected utility, which the way we've set things up is just, well, it's just the weighted accuracy on this data set, right? It's just the weighted fraction of points that we predict correctly, because the cost function is just the indicator of whether we predict a point correctly or not. Okay. So this expression that we get when we sort of write down the min-max value of the game, right? It's just the minimum over distributions over the data points, over weightings of the data points, of the maximum over hypotheses, of the weighted accuracy of the data set under that weighting. And remember, like, what was the object we were given? It was a weak learning algorithm. And what a weak learning algorithm promised was exactly that no matter what weighting of the data set we were given, it would produce a hypothesis that does a little bit better than random guessing, right? That predicts a little bit better than a coin flip, that gets accuracy 51%. Okay, so in particular, for whatever weighting the data player chooses to play, if they go first and tell it to us, one way we could imagine responding to that was by just feeding that weight vector into our weak learning algorithm. And the weak learning algorithm has the promise that it will give us a hypothesis that has weighted accuracy at least 51%. And so the min-max value of the game can only be bigger than that. Does that make sense? Okay, so we've written down this game, and we're curious about the value of the game. It's often easier to think about the value of the game in one of the orderings of play compared to the other. We've chosen to think about the ordering of play in which first we're given a distribution over the data, and then we get to pick the hypothesis. And we can think about the weak learning algorithm as basically a best response oracle in this game. It tells us, given a distribution over actions of the data player, how should we pick a hypothesis that has high accuracy, that maximizes the accuracy, in this case, the cost in the game, and it's at least 51%, because we have a weak learning algorithm. Make sense? Okay. So, if the adversary goes first and tells us a weighting over the data set, the learner in this game can best respond and get predictive accuracy at least 51%. But that's not really how we're interested in playing the game. We want sort of ultimately a learning algorithm that sort of always does well. But what the min-max theorem tells us is that, well, the min-max value of the game is equal to the max-min value of the game. In a zero-sum game, it doesn't matter who goes first. So in this case in particular, that means we can reverse the order of play. We can say, okay, first, we can imagine the learning, first we can imagine the learner having to commit to a mixed strategy, which in this case is a distribution over hypotheses. After the learner has committed to this distribution over hypotheses, the data player can pick a single data point, can pick the worst data point for this distribution over hypotheses, the one that minimizes expected accuracy. Right? So then the data player picks the data point that minimizes in expectation over the mixed strategy of the learner, the probability that the learner's hypothesis gets the answer right. Okay, that's just the game described with the order of play reversed. First, the learner commits to a mixed strategy, which is a distribution over hypotheses. Then the adversary best responds, they pick a data point, and the value of the game is the same in this ordering as it was before. So if both players play optimally, the learner has a distribution such that for every data point, for at least 51% of the hypotheses under the learner's distribution, that hypothesis gets the answer correct. Okay, so just saying that again, there is a fixed distribution. Let's call it P star. It is the max-min strategy for the learner in this zero-sum game we've just defined that has the following properties. So first of all, like, what kind of object is this? Well, it's a distribution over hypotheses. Like if our weak learner outputs decision trees, this is a distribution over decision trees. And the property that it has is that for every single, since it's a max-min value, right, it's promising something in the worst case for actions of the adversary. In this case, actions of the adversary correspond to data points. And so the promise is for every single data point in our data set, at least 51% of the probability mass of P star, this distribution over hypotheses, is put on hypotheses that predict the correct label for this data point. That's true for every single one of the data points. Okay? This was like an important switch, but all that's, the way we're doing it is we're just applying the max-min, the minimax theorem. Right? The min-max value of any zero-sum game, including this one, is equal to the max-min value. Okay, so just to like emphasize this switch, this is where all the action is happening. We went from the weak learning statement, which said for every weighting of the distribution, there exists a hypothesis that gets 51% accuracy, to this reversed statement that says there is a single weighting of the hypotheses, there's a single distribution over hypotheses that for every example gets 51% accuracy. Okay, that's what happens in this case when we switch the min and the max. Does that make sense? Questions? If I'm slipping a fast one by you, it's here. So ask questions. Yeah. Yes. So what we now have is like a randomized way of coming up with predictions, right? So like each of these hypotheses, they map images to predicted labels, hot dog or no hot dog. But now what I've got is like, it's a mixed strategy for the learner. So it's a distribution over hypotheses. So for every example, it maps to like a distribution over predictions. Some fraction of them predict 1, some fraction of them predict 0. And the claim is that for every example, at least 51% of them predict the right answer. Yeah. Yeah, good question. Right. So I mean, yes, right. So as described, this only makes sense if, in principle, it is possible to correctly label examples. I mean, in fact, what's the theorem we're proving? Right. The theorem we're proving is that the theorem we're in the middle of proving is that if you give me a weak learner, then I can give you a strong learner, which gets perfect accuracy. And of course, that's not possible if I have two examples that are observationally equivalent. All of the features are the same, but they have different labels, because if I get one of them right, I'm going to have to get the other one wrong, and vice versa. You can extend all of that to this case, but yes, and the way I've defined everything, this only makes sense if you never have the sort of exact same feature vector with two different labels. And in high dimensional settings, that's generally the case. Like there's a lot of, even though hot dogs all look kind of similar, like if I take a, picture of a hot dog with my phone, like actually there's quite a lot of pixels, and it's, you would never see exactly the same image twice. Yeah.
So why before the variable p sub h, why was that w? Why did we change that?
Oh, so when we were looking at the min-max value, we were looking at the expected cost over the mixed strategy of the data player. The mixed strategy of the data player is a weighting on the data points. We called those W. Here, we're looking at the expected payoff in expectation over a mixed strategy of the learner. The mixed strategy of the learner is a distribution over hypotheses. I'm calling that P. Yeah. Yeah, so basically, like, I'm not going to talk about this, but that is exactly how you fix this problem of there not being a perfect classifier because there being like mislabeled points. You would sort of limit the data player to having to play distributions that are like not too concentrated on any single data point. And you can do all of that, but there are variants of the polynomial weights algorithm, for example, that do that guarantee they don't focus too much weight on any single point. That is, in fact, how you solve this problem of there not being a perfect classifier, but we won't talk about that. Good question. So is all of this, yes?
Maybe as an example, the assumption is that across all the victims in the hypothesis class, at least 51% of that correctly size. But is there any bound size what the percentages are? Modeling. The case where, let's say, there's 4 different data points. 3 out of 4 that work, then 4 out of 4 that correctly.
Maybe I didn't quite understand the question, but is it about difference between data points in the data set versus data points not in the data set?
I guess it's like guaranteed at least 51% of the problem mass correctly data set. Is there kind of balance on size of data set?
Well, like the assumption that went into this was the weak learning assumption. This follows just from the min-max theorem. The weak learning assumption, the way we stated it, was an assumption for a particular data set. So it said on this data set, you have a weak learner if for every weighting of the data points, you can get better than 51% accuracy. Okay. So consider the following classifier. Okay, like by the way, like so far, we haven't said anything that sounds like strong learning. Like we've gone from a distribution over data points to a distribution over hypotheses, but like the accuracy numbers we're talking about are still 51%. However, consider the following classifier, right? Suppose I compute this vector P star, this distribution over hypotheses. I can do that. That's just the min-max equilibrium strategy for this game, for the learner. I'm going to use this probability vector, this distribution over hypotheses, to define a majority vote classifier. What am I going to do? Well, given an example X, I'm going to compute what fraction of the probability mass under this distribution predicts that X has label 1, and what fraction of it predicts that X has label 0. And I'm going to take the weighted majority vote. We've seen this before in the weighted majority algorithm. So if more than 50% of the probability mass under this distribution predicts label 1, then I will predict label 1. Otherwise, I will predict label 0. Okay, weighted majority vote, where the weights come from the min-max equilibrium strategy for the learner in this game. The classifier makes sense? Then the claim is that this classifier that takes the weighted majority vote over a bunch of weak learners, well, this must be a strong learner, must have perfect accuracy. Each H is in the hypothesis class of the weak learning algorithm. Okay. So let's just observe that, like, and just to be clear, like, we haven't given an algorithm yet. So far, we're just analyzing like things existentially. Like, we don't know how to like compute this just yet. We'll get there. But let's just observe that this thing must have perfect accuracy, right? And that follows pretty immediately from this sort of min-max guarantee, right? Because the min-max guarantee was that for every data point, 51% of the probability mass of the hypotheses under this distribution predicted the right label, and we're just taking the weighted majority vote under this probability distribution. Okay. So the claim is, if we take the distribution P star, that is the max-min equilibrium strategy for the learner in this zero-sum game, and then we compute the classifier that takes this weighted majority vote, it's got perfect accuracy. Okay, how come? Well, let's fix any data point. We need to show that this weighted majority vote classifier predicts the label correctly. Well, we know from our min-max calculation in this game that for every data point, the fraction of the probability mass that's put on hypotheses that predict the correct label is at least 51%. So if the label's 1, that means that the fraction of the probability mass that predicts 1 is at least 51%, and our classifier just thresholds at 50%, so we predict 1, so we're right. And similarly, if the true label is 0, it must be that the fraction of the probability mass that predicts 1 is at most 49%, and we threshold at 50%, so we predict 0, and again, we're right. So we're right on every example. That's it. Okay. So, okay, what have we done so far? We've proven that the existence of a weak learning algorithm is equivalent to the existence of a strong learning algorithm. If it's possible to predict with 51% accuracy on any distribution over data points, then it's also possible to predict with perfect accuracy on the same distribution, on the same data set. But like, what's the efficient algorithm? I claimed something stronger than that, not just this existential equivalence, but actually like a computationally efficient reduction. That if you give me a weak learning algorithm, I have a computationally efficient strong learning algorithm. And one thing you might worry about is that, you could say, like, we know how to compute the equilibria of zero-sum games. All we need to do to compute this threshold strategy is to compute the min-max equilibrium strategy for the learner. But the learner has a ton of hypotheses, potentially, right? Like, suppose I have an efficient weak learning algorithm. What it's doing is, some heuristic for learning decision trees. Well, in this game I just defined, like, the action space for the learner is the set of all decision trees. That's enormous, right? So like, this is a huge game. It's not at all obvious that I can just like compute the equilibrium strategy for this game. But of course, if you give me the equilibrium strategy, right, if you give me this distribution over hypotheses, at least if it doesn't put weight on too many different hypotheses, then the strong learning algorithm is simple to compute. It's just this weighted majority vote. So the algorithmic problem is to compute an equilibrium strategy for the learner in this zero-sum game we've just defined, using only a small number of calls to our weak learning algorithm as a subroutine. And hopefully it'll generate for us a weighting of the hypotheses that puts zero weight on most of the hypotheses, so that computing this weighted majority vote isn't too hard. I only want to have to enumerate like a small number of things. Okay, so that's what remains. Yes. Oh, because what was this thing? It was just the weighted majority vote. So I just, if you give me this vector that puts a weight on each hypothesis, and maybe also it only puts a positive weight on like a small number of hypotheses, then what do? I just compute for each of the hypotheses this thing puts a positive weight on, the prediction of that hypothesis, and then I just like sum up the weights, and I see if it's, if the weights on hypotheses that predict one is greater than 51% or not. So the hard problem, it seems, is computing this like P star that is like an equilibrium strategy and doesn't put weight on too many different hypotheses. Yeah. That's right. Yeah. And in fact, if you sort of think about the argument, right, like the value of the game is like 51%. But like, when we argued that our classifier had perfect accuracy, it was like thresholding at 50%. So there was like a little bit of slack between 51% and 50%. So we don't actually need to compute an exact equilibrium for this game. It's enough to compute an epsilon approximate equilibrium for epsilon less than 0.01. We just need that on every example, strictly more than 50% of the weight is on hypotheses that produce the correct label. And so we know how to do things like that, right? Like, remember, we studied like learning dynamics in zero-sum games, and we proved they converge to approximate equilibria in zero-sum games. And there were a few ways to do it, right? Like, ultimately, all we needed to do was simulate play of the game so that both players had regret less than epsilon. So one way we could do that is we could have both players play the polynomial weights algorithm. That would be okay for the data player because, like, he only has to maintain one weight for every data point. He only has n actions in this game if the data set's of size n. But that would be like a huge pain to do for the learning player, the learner, because his action space is potentially enormous, one for every, say, decision tree. He'd have to maintain a ton of weights. But there was another dynamic that led to both players having no regret. This was actually the dynamic we used when we proved the minimax theorem, which was to have one of the players in the game play the polynomial weights algorithm, and the other one every day to look at the mixed strategy of the polynomial weights player and to then best respond to it. One player plays polynomial weights, the other player plays best response. This also leads to both players having no regrets. This is actually how we prove the min-max theorem. And so we can have the data player play polynomial weights, just maintains a weight vector over the n points in the data set. Have the learner play best response. And we know how to have the learner play best response. We run the weak learning algorithm. And so the algorithm is something we've seen before. We just simulate play of this game. To compute an epsilon approximate equilibrium with polynomial weights, how many rounds do we need to run for? Well, just log n over epsilon squared many rounds. And epsilon here is a constant, because we only need epsilon to be less than 0.01. So we run this dynamic for only log n many rounds. The data player is playing polynomial weights. They're maintaining a weight vector over the data points, n data points, a weight vector of length n. Every day, the learner, they best respond to the mixed strategy implied by the data player's polynomial weights distribution. How do they do that? Well, they just run the weak learning algorithm on the data set given the weight vector from the polynomial weights algorithm. That gives us our best response, which means for every action of the data player, we can compute the loss. That's just the indicator of whether this round's weak learning algorithm misclassified the example or not. That's what we need to update the polynomial weights algorithm, this loss vector. And then at the end, what is the thing? What is the object that is the approximate min-max strategy for the learner? Well, it's just the uniform distribution over the hypotheses played by the learner over the course of this algorithm. So it's just like a uniform distribution over these hypotheses HT. This is a distribution over hypotheses that happens to be sparse. It happens to put weight on only log n over epsilon squared many hypotheses, because every round the learner played one hypothesis and we're just output, there's only log n over epsilon squared many rounds. So this distribution over hypotheses we output at the end, it puts weight 0 on almost everything. It only puts positive weight on log n over epsilon squared many hypotheses. Those hypotheses that were were produced by the weak learning algorithm over the course of the run of this algorithm. Okay, so the algorithm is just weight the data points, run the weak learning algorithm on them, reweight the data points using the polynomial weights update rule, run the weak learning algorithm, repeat for log n rounds, output in the end the equilibrium strategy that corresponds to the uniform distribution over the hypotheses output by the weak learning algorithm.
Why now we're like just put the min-max.
Yes, so what this outputs, right, is an approximate min-max strategy for the learner in this game, a weighting over hypotheses. And remember, our final strong learner is just a majority vote over this weighting. Okay, so like actually, we just get a list of log n over epsilon squared many hypotheses, just the list of hypotheses output by the weak learner while we run this algorithm, right? So our weighting is actually just, uniform over this list. And so our final majority vote classifier, all we do on a new example is we feed the example into every one of the log n hypotheses output in this list. And if 51%, if at least 50% of them predict 1, we predict 1, otherwise we predict 0. So it's actually an extremely simple prediction rule at the end. It's just a majority vote over the log n hypotheses output by the weak learning algorithm in this dynamic. The weak learning guarantee is that when we run our weak learner on, here, the classification accuracy as measured by, our weighted classification accuracy as measured by the weights we plugged into the learner is 51% at least, a little bit better than random guessing. Okay, so each of these hypotheses was good, a little bit good for the weight vector that we used to generate it, not necessarily for any other weight vector. Okay, the algorithm makes sense. So this is a computationally efficient algorithm, right? Since we only need an epsilon approximate equilibrium for like a constant value of epsilon, our data sets of size n, this algorithm runs for only log n iterations. At each iteration, we make only a single call to the weak learning algorithm. We have to update the polynomial weights distribution, which is a weighting over n data points that takes linear time. And so if the running time of our weak learning algorithm is R of A, we've just given like a wrapper algorithm that calls it as a subroutine a small number of times. The running time of this algorithm is only log n times the running time of the weak learning algorithm plus n, the overhead of updating the weights. Okay, so if the weak learning algorithm was computationally efficient, so is the strong learning algorithm. Okay. And sort of briefly again to mention sort of the statistical aspects of this. You remember, like really, if all we wanted to do was predict the labels in the training set, we could have just written them on our hand, right? Like that's not hard. The thing we really want to do is predict labels for examples we haven't seen before drawn from the same distribution. And I sort of waved my hands and said, well, like if you took a course in learning theory, you'd sort of learn all sorts of theorems that had the form, if you can make simple predictions that are accurate on your data set, they're also accurate on new examples drawn from the same distribution. Okay, so somehow generalize, squinting your eyes a little bit, generalizing to unseen data happens for free if the rule you learn is simple. Now, we've assumed that our weak learning algorithm is a weak learning. So if the distributional version of a weak learning algorithm is that it gets 51% accuracy on new examples out of sample. Okay, so presumably the hypotheses learned by the weak learning algorithm, those are simple in whatever way is necessary for generalization. Now the thing we produce in the end is just a majority vote over log n of these hypotheses. So like it's not much more complicated, right? Like if the hypotheses in H are simple, our hypothesis that we come up with at the end can be described as just, a list of log n of these hypotheses, just a set, even the ordering doesn't matter. And so informally, the amount of data you need to generalize to new examples for strong learning out of sample is not much more than the amount of data you need just for your weak learner to generalize out of sample, because we haven't, like the algorithm we've produced has not increased the complexity of our prediction rules by very much. We started with simple prediction rules. What we come up with is just a majority vote over a small number, log n, of those simple prediction rules, which is also simple. So you can formalize this by using words like DC dimension, but I won't cover that. Questions? So in the setting in which we analyzed it, it is guaranteed to get 100% accuracy. Now, oh yeah, because right, our argument that we get 100% accuracy, it didn't require that we had an exact equilibrium, right? An exact equilibrium would get the right answer 51% of the time at least. Our argument only required that we got the right answer more than 50% of the time. So anything less than a 0.01 approximate equilibrium was good enough. Now, one way to interpret this rather than a positive result is like a negative result. Like obviously perfect prediction is like super hard. So like maybe maybe like calling this thing a weak learner was misleading, right? Like weak learning is as hard as strong learning. And indeed, like weak learning is as strong learning. Like putting this universal quantifier there made it a strong assumption. The fact that the weak learner had to get 51% accuracy on every single distribution made that a strong assumption, as strong learning. But our algorithm doesn't actually require that the weak learner work on every distribution. It only has to work on the log n distributions that we happen to feed it. And so it makes perfect sense to run this algorithm and see if it works. And in fact, it works great. This algorithm is basically what's called AdaBoost, which is a very good algorithm. It doesn't get perfect accuracy, but it very reliably increases the accuracy of simple learning techniques. All via game theory. So normally I see you next class, but this is the last one. So have a great summer.